Experiment 19 in Chem 1212 is titled Exploring Buffers and Buffer Capacity. And in this experiment, you're going to design a buffer system and then test the ability of that buffer system to resist changes in pH when strong acids or bases are added to it. This is really the advantage and the purpose of buffers, that they are very stable to the addition of strong acids or bases. So they have all kinds of applications in laboratory chemistry and beyond for maintaining the pH of a mixture, for example, a swimming pool. In this video, I want to give you a theoretical foundation that helps you design your own buffer and predict what the change in pH is going to be when strong acid or base are added. Ideas from equilibrium that you already know, that you already understand, can be applied to the relatively complicated but still parsable buffer system to figure out theoretically what the pH of a buffer is going to be based on the concentrations of its components, and what the change in pH is going to be when strong acids or bases are added. This will give you a feel for what to expect in the laboratory, and this way you can hit the ground running with designing your buffer as soon as you set foot in the lab. Let's begin by talking about what a buffer is, starting at a very basic level, discussing its chemical components and how to determine its pH based on the concentrations of those components. So to make a buffer, essentially all we need to do is start with a solvent, start with water, and add to the water a weak acid, HA, and its conjugate base, A-. It's very important that the acid be weak, and it's very important that we either add directly or somehow generate approximately equal concentrations of HA and A-. They can differ, but there need to be substantial amounts of both HA and A- in the system. So simply adding a weak acid to water won't generate a buffer. The resulting mixture is really a witch's brew of all kinds of different components, and it's one of the most complicated chemical systems that you'll see in Chem 1212. We of course have the typical players in any aqueous solution of liquid water, hydronium ion, and hydroxide. But in addition to these three components, we also have the acid HA and the conjugate base A-. The hydronium ion concentration, we know this already from experiment 18, is related to the pH. pH is equal to the negative log of the hydronium ion concentration. And a big question with buffers is, how can we design a buffer system to achieve a desired pH? So in addition to being able to resist changes in pH, we can tune the buffer to sit at a particular pH value. The key to that is the weak acid equilibrium. This is really the most important chemical equation to keep in mind when dealing with buffers. It's the acid dissociation of the weak acid HA. So on the left we have the aqueous HA reacting with water, and on the right we have the conjugate base A- and hydronium ion H3O+. So in the forward direction, this reaction generates H3O+, and in the reverse direction it consumes H3O+, and thereby indirectly generates hydroxide through the self-ionization of water. The key to really designing a buffer system comes in when we think about the concentrations of HA and A-. If we write out the equilibrium expression for this key equilibrium for a buffer system, we find that in the numerator we have the products, the concentration of H3O+ and the concentration of A-, and in the denominator we have the concentration of HA, the reactants. So we see that because Ka is a constant, we can play with the ratio of A- to HA to affect the concentration of H3O+ and thereby the pH of the buffer solution. So another way to express this is to take the negative base 10 logarithm of both sides and then do a little bit of rearranging to obtain that the pH is equal to the pKa of the weak acid, the pKa of HA, the weak acid component, plus the base 10 logarithm of this ratio A- over HA. And that's critical. It tells us again that we can control the buffer's pH by adjusting this ratio of A- to HA in solution. Often when you'll apply this equation, you'll use initial concentrations. In other words, you'll use concentrations based on the number of moles of HA and A- you add and the total volume of the solution, not taking into account any equilibration of HA and A- via this acid dissociation equilibrium. That's a little bit dangerous and a little bit dicey, right? Because we haven't factored in the value of Ka, we haven't factored in coming to equilibrium, and we've just used the initial concentrations directly, which could, in some cases, be very different from the equilibrium concentrations of HA and A-. However, it's a pretty good assumption that the initial concentrations are roughly equal to the equilibrium concentrations, particularly when the Ka value is much, much less than the initial concentrations of HA and A minus. The changes are much, much smaller than the starting initial concentrations, so the equilibrium and initial concentrations are roughly equal, and the concentration of HA and A minus will shift very little after we add them in. So again, it's pretty much okay to use initial concentrations provided Ka is much less than the initial concentrations of HA and A minus, and this is definitely going to be true in experiment 19. In cases when it's not true, you can use an alternative approach that in many ways is more rigorous, and that involves using an ice table. So I want to show a quick example of that and illustrate how an approximation comes in that allows us to use this equation you see on the right, the Henderson-Hasselbalch equation. So let's put some numbers to this and say we started with 0.1 moles per liter of HA in solution and 0.08 moles per liter of A minus in solution, and we can imagine that both components are added simultaneously before we ever think about chemical equilibrium. And when you do buffer problems, I encourage you to think this way. Here the H3O plus concentration is fairly small, so it's reasonable to assume that the reaction is going to go to the right. If you really wanted to check this and do what you really should do, you have to compare Q based on these initial concentrations of HA, A minus, and 10 to the negative 7 moles per liter of hydronium to the Ka value. Got to do a Q versus K calculation and figure out which direction this equilibrium is going to go. But just for the purposes of illustration, let's say it goes to the right. So we can add the initial and change lines to get equilibrium lines, and then doing the usual ice table routine, we can plug these into the equilibrium expression. Before we do this, again, provided that Ka is quite small relative to these initial concentrations, which for a weak acid it will be, we can assume that X is small. So the equilibrium concentrations will be roughly equal to the initial concentrations. And this is where that approximation in the right-hand equation, in the Henderson-Hasselbalch equation, comes in. These equilibrium concentrations in red are essentially equal to the initial concentrations shown in blue. So when we plug into the equilibrium expression, Ka is equal to the hydronium ion concentration times, again, approximately the initial concentration of A minus divided by approximately the initial concentration of HA, and from there we can go on to solve for H3O plus concentration and the pH. Where we can make these approximations, this approach is equivalent to using the Henderson-Hasselbalch equation. But when we cannot, the ice table approach shown on the left is more rigorous than using the initial concentrations on the right. That's going to introduce some error in every case, but often the error it introduces is so small that we can ignore it. For example, if the difference is less than the precision of our measuring instruments, which is going to be the case when you get into the lab for experiment 19. So now that we understand how to tune the pH of a buffer by adjusting the ratio of A minus to HA, let's talk about what happens when we add strong acid or base to a buffer. So let's imagine that we had a hypothetical buffer system with these generalized concentrations: HA sub I for initial, A minus sub I, and 10 to the negative pH. And this is a buffer, so HA sub I and A minus sub I are substantial numbers. What happens when we add a strong acid to this system? Well, a strong acid essentially is H3O plus once it dissolves in solution. And this H3O plus can react with the conjugate base present in the buffer, A minus. Let's assume that we have more A minus than the amount of H3O plus that's added in, so that this reaction can proceed fully to the right. That's an important thing to notice, that this is 100% conversion of A minus to HA. That happens because H3O plus itself is a very, very strong acid. So it surrenders a proton completely to A minus, and essentially all of the A minus that can react with the added H3O plus gets converted into HA. This leads to a new set of initial concentrations, which I've labeled with primes here. There are a few things to notice about these new initial concentrations. The first is that the new HA concentration is higher than the HA concentration in the buffer. So HA prime sub I is higher than HA sub I. That's because the acid has converted some of the conjugate base to the acidic form, converted some of the A minus to HA. The second thing to notice is that A minus prime sub I. The new conjugate base concentration is lower than the initial concentration of A minus in the buffer, which is shown here in red. And that's because the added acid consumes or reacts with A minus to form HA. A third thing to notice is that the H3O plus concentration in this new initial line has not changed. That's because we've kind of thought about the H3O plus that's present in the buffer initially as completely separate from the H3O plus that's added as the strong acid. So we can consume all of the added H3O plus through the complete reaction that you see on the right here and leave the H3O plus that was present in the buffer initially untouched. These three things that we've noticed about this black initial line point to the idea that this is not an equilibrium state. To figure out what the pH is going to be at equilibrium, we need to essentially allow this non-equilibrium solution to settle out into a final situation where the equilibrium expression for this acid dissociation equilibrium in blue is obeyed. So to do that, the next step is to generate the change line. And we can start by just writing a variable here. We don't know what this is, and the goal of this, like the goal of many ICE table problems, is to figure out the value of x and ultimately the value of the H3O plus concentration and the pH. So because the stoichiometry is just 1-to-1 across the board, we can write x's without any coefficients here. And now the question becomes what to do with the sign of x. In other words, which direction is this reaction going to go predominantly? The way I like to think about this is to again think about the values of HA prime and A minus prime after addition of the acid. What the acid does is it converts a product of this equilibrium into a reactant. So we've decreased a product concentration and increased a reactant concentration. This means that Q corresponding to that I line is less than the Ka value, which implies that the reaction will proceed in the forward direction and will lose HA, so there's a negative change there, and will gain A minus and H3O plus. We can then do the typical equilibrium step of adding the I and C lines together to generate equilibrium concentrations that contain this X variable, and we can plug these into the equilibrium expression. So Ka is equal to A minus prime plus X, 10 to the negative pH plus X, and then in the denominator we have the reactant HA prime minus X. And our final goal ultimately is to find the equilibrium concentration of H3O plus. This is going to give us the pH at equilibrium of the buffer after the acid has done its thing. Now if x is small, which it will be if the concentrations on the I line are all much greater than the Ka value, then we can make a useful simplifying assumption, which is that these factors that contain A minus prime plus x and HA prime minus x are really approximately equal to A minus prime and HA prime. So we can essentially remove the plus x and the minus x from those factors and simplify this Ka expression to Ka times HA prime divided by A minus prime, the initial concentrations, notice, is equal to 10 to the negative pH plus x. And this is equal to the equilibrium concentration of H3O plus. This is a pretty simple calculation. Ka we know, or we can look up. HA prime we know by, again, adding the initial concentration from the buffer to the HA generated through the irreversible reaction on the right. And A minus prime we can find by subtracting the A minus that was consumed by this reaction from the initial A minus present in the buffer. So all three of the pieces on the left-hand side of this equation are numbers that we can find fairly easily without doing any sort of complicated math. And this is equal directly to the concentration of H3O plus. I won't do it here, but something that's worth noticing is that if you take the negative logarithm of both sides of this equation at the bottom, you arrive at the Henderson-Hasselbalch equation, and it shows you that you can use the HH equation in conjunction with the concentrations on the I line to calculate the pH of a buffer after the addition of strong acid or base. And this all hinges, as it did in our first calculation of buffer pH, on the fact that x is small so that we can neglect the contribution of x to the equilibrium concentrations for HA and A minus. For adding base to a buffer, the situation is analogous, except we're going in the opposite direction in terms of this complete reaction. So HA now is being consumed through reaction with the added base. This is a 100% complete reaction. So all of the hydroxide reacts completely with HA to form A-. In this case, we've removed a reactant and we've added a product to the buffer, and thus Q is greater than Ka, and the equilibrium is going to move back to the left. So the signs of X will change, but the basic process will still be the same. Finally, let's quantify the ability of a buffer to resist changes in pH by discussing buffer capacity. So the key question with buffer capacity is, what's the change in pH when we add some number of moles of H3O plus or hydroxide to a buffer solution? For a good buffer, the delta pH value should be relatively small. We'll talk about what relatively small means and what our point of reference will be for this experiment shortly, but it should be relatively small for a buffer because buffers can resist changes in pH. We can quantify buffer capacity by looking at the ratio of, say, the number of moles of acid added to a buffer divided by the change in pH. We might call this C sub A, or the acid capacity. Similarly, we can write a base capacity, C sub B, as the number of moles of hydroxide added divided by the change in pH, delta pH. For a good buffer, these values will be large because it will take a lot of moles of acid or base to cause a unit change in pH. However, the two values are not likely to be equal to each other for a given buffer. In fact, there's only a very specialized situation where we would expect C sub A and C sub B to be equal to each other, and I'd encourage you to think about what that situation is. In the actual experiment, you're going to run 4 capacity tests for each buffer, 2 for acid and 2 for base. You're going to start with a volume of buffer V in one beaker and an equal volume of water in another beaker that's going to serve as a control. You're then going to add in a small number of moles of acid, let's say, or base, into the buffer, and the same number of moles of acid into the water. You want this to be relatively small for 2 reasons. One, you don't want to break the buffer. You don't want to use more moles of acid than you have moles of conjugate base of the buffer available to react with it. And 2, you want to keep the volume after the addition of these acidic or basic solutions very close to the initial volume so that you can make the approximation that the volume of the system doesn't change after addition of the strong acid or strong base. Before and after adding the acid to each of these solutions, you're going to measure the pH, and so you'll obtain a change in pH for the buffer, delta pH buff, and a change in pH for the water, delta pH H2O. You're then going to compare the acid capacity of the buffer to the acid capacity of water. Clearly, if the buffer is a good one, the acid capacity of the buffer should be greater than the acid capacity of the water. In other words, it should take more moles of acid to change the pH by 1 unit for the buffer than it should for an equivalent volume of water. And the statement about an equivalent volume is important. It's critical to use the same volume of buffer and water. Using a greater volume of one or the other changes how the solution responds to pH. So it's important to make sure that you use equal volumes of buffer and water. You'll do the same for base and compare the C sub B of the buffer to the C sub B of water. Here again, if the buffer is a good one, is good at resisting strong base, then the base buffer capacity of the buffer will be much greater than the base capacity of water. One experimental note on this, you only need to add 1 number of moles of acid and base to buffer and water. So don't go about titrating your buffer or water with strong acid or strong base. You only need 1 volume, 1 milliliter in 20 milliliters of buffer, 1 milliliter in 20 milliliters of water, and you're good to go.